First of all, I apologize a little bit for my voice. I'm feeling a little under the weather today, so I'll try to do my best. So today I'm going to present the work that I've been doing in the part of the last year, which is regarding the testing of the different propellants for our thruster, Athena. So first, the motivation, I think, is quite clear from my colleague. At Athena Space, we're trying to develop a high efficiency and low power system based on electrospray technology. Myself, I'm going to focus a little bit more on the physics, so how electrospray work. We have the propellant management unit. We have basically like three systems here. We would say like the management unit. We have the emitter and the extractor. The management unit contains the propellant, which in our case is an ionic liquid. We have the emitter, which is microfabricated in silicon and features these emission sites or cones, and the extractor, which is aligned with the different emission sites. When we apply a potential difference between the extractor and the emitter, the particles climb to the top of these cones, forming what is known as a Taylor cone, from which the particles are extracted from the liquid and accelerated by the same potential that we are applying with respect to the extractor. One thing that is important to know about electrospray, I think Borja mentioned before in the question that Eduardo asked, is that we have different type of particles in the plume. So depending on different conditions, on the electric field and the flow rate, we will have a different composition. We can have only ions, which can be either monomers, dimers, or trimers, depending on the configuration, or droplets, which are a cluster of these ions. It is important to know because most of my work and the performance that I derive and all the results are based in this explanation. But the main focus of this presentation is on the ionic liquids. Why do we use it, and why are they are basically the key for electrospray. First, they are self-neutralizing, so they are composed of both the positive and negative molecules. So by applying the positive or negative voltage, we can extract either positive or negative, and we can achieve a neutral plume by alternating these polarities without the need of an external cathode. Also, they are stable in vacuum. They are safe handling. You can use them in the lab with some goggles and some gloves. You don't need anything else. They work with just an electric field. We don't need any magnetic elements. Both the extraction and the acceleration is done by the same electric field. We don't have the losses that the plasma really losses, but we do have, as we mentioned before, this polydispersity losses. And also, one thing that is important thing nowadays is the propellant accessibility. We get all the propellant from suppliers here in Europe, which now with the war and stuff with China stuff is difficult to get other propellants like xenon. So the goals and methods for my thesis, first of all, was to build a suite of diagnostics to test this electrospray thruster. This was done in the first year, along with the characterization of the thruster based on different variables like the voltage or the temperature. This was presented last year in the doctoral meetings, and I will talk at the end a little bit more about how all this work came to an end. And today I'm going to focus on the analysis of the different propellants, and later on the last task will be to build a tomography to analyze other things like the startup configuration of the thruster. So talking about the ionic liquids, we are using MIM as the Athena baseline. We use this because it has flight heritage. It is widely understood in the electrospray community. It doesn't absorb water, which is a bit of an issue when you're working with it in the lab. And we found that the performance meets the requirement. That means that it is acceptable for what we said, but of course it can be improved. We find that the positive and the negative emission is a bit different. Therefore, we have to make some effort into compensating. Also, it has a low conductivity, which results in a lower emission, which at the end we will see that it results in a lower thrust. And we find droplets in the negative emission, and this will be a drawback mainly for the polydispersity efficiency. So the different liquids that I've been testing are these four: MIM, MEOTF, MESCN, and METFA. I'm giving here some of the important parameters. because basically, so you have an idea, the higher the surface tension and the higher the conductivity, the more emission you will get, therefore the higher thrust you will get. And for the viscosity, this was one of the results that we found with the previous work, is that if we have, for kind of emitters, if we have a really low viscosity, we will find more droplets than with a high viscosity system. So therefore, we were trying to vary these values of viscosity and conductivity to see how the different parameters of the propellant influence the performance. Just an interesting note about this ionic liquid, MESCN, is an apergolic liquid. That means that can be also used for chemical propulsion, as it can ignite. So it could be interesting in the future for a dual system that use both chemical and electric using the same propellant. So the work is based on mass flight spectrometry. So just briefly, I will explain how it works. We have here our thruster, a deflection gate, which is driven by a high voltage pulse generator. When we apply this pulse to the gate, all the particles will be deflected to an angle so they cannot reach the collector. And only the particles that have passed already the gate will arrive at the collector, because, as I said, we have different particles, different masses, they will have different velocities, and they will arrive at different times. At the end, we get a curve something like this, where we see here the monomers step, dimers, trimers, and then droplets. And this is an ideal curve of how it would look. This is the actual curve that we get with our instrument. And here we can see that we have this distribution with the distribution of droplets. How we translate these curves to the actual parameters? So these are the equations. We can integrate this curve to obtain both the thrust, the mass flow, from which we get the ISP, polyspecificity efficiency, and finally we can get the thrust efficiency if we take into account other efficiencies like the angular efficiency, which I'm not going to show here, but it's usually we have around 80% of angular efficiency. Energy efficiency is around 98% in electrosprite, or most of the electric field that are given to the particles. Like, we have almost no energy losses. Most of the losses, they come from the polyspecificity, so from the fact that they have different masses, and the intercepted, or the efficiency, which is the amount of current that is intercepted by the grid instead of going out of the thruster, and we have usually around 99%. So this is our setup that we have. This is a half a meter cube chamber with the extension tube for the time of flight. Just to have an idea how big the thruster is, so this is a size of the lab prototype that I was using. So the active area is 1 centimeter by 1 centimeter, so quite small. And the results that I'm going to show here, they are varying the apply voltage from 1000 to 1600. So comparing both the four liquids, we see that the highest emitted current is given by the MESCN. This is explained by the conductivity. I think I didn't mention, but it has the highest from the four liquids. It has the highest conductivity, so this is why we find a higher emitted current, while the one that we use, MIM, has the lowest, of course, because of this low conductivity, which is one of the things that we're trying to improve. But nevertheless, like, we see that the power that this is the emitter power is still like quite low, it's tenths of a watt for any of the liquids. If we move to the thrust, we find that for MIM we get around 6-7 micronewtons, while for example for SCN, which has of course the highest conductivity and highest current emitted, we get a bit more than 10 micronewtons. As for the specific impulse, we get that the MESCN has the highest. This also has to do to the fact that the different molecules of the SCN, they are lower in mass, so they are accelerated more, giving therefore like a higher specific impulse. For the other liquids, MEOTF, METFA, we find like they are really similar between each other, like in terms of thrust to power, even the specific impulse. So I'm not going to comment much more on those, because they are not, from the result that we found, they are not that interesting. They are similar in performance to the MIM, but we have even less data about it. And if we look at the polyspecific efficiency, on the other hand, we find that the MIM is the best, and this is one of the reasons why we're using this liquid. Of course, because the MIM has real different size in the size of the particles of the ions and the droplets. The difference is quite high, and the polyspecificity efficiency measures like how dispersed these are. So the closer the masses of both the ions and the droplets are, the higher the the polysphericity efficiency will be. Therefore, this is why we're sticking with MIM for the moment, because we find that for the overall efficiency, we yield a higher value, but of course we still need to improve those values of thrust, or the specific inputs could be a bit higher, which can be done by other techniques, but here I'm just using the same thruster and trying to analyze different propellants. So some of the conclusions from this work, we find that MIM has the highest thrust efficiency of all the liquids, and this is why we are using it, and NI, but it lacks thrust due to the lower emitted current. This can be done by increasing just the electric field. We can get a higher current, but of course we are increasing the electric field is not an ideal solution for the system. As for MESCN, we find it has the higher thrust and specific inputs, but has a lower thrust efficiency. This can be done by increasing the fluidic impedance. So increasing the fluidic impedance, since the mass flow is controlled passively by the emitter, we need to control this value of the fluidic impedance to reduce the flow rate below a certain value, so we can get this ionic emission. And as for MEOTF and METFA, we find that show similar performance. They are close in thrust and specific inputs, but in thrust efficiency they fall short to the norm of MIM. And I also wanted to highlight how easy and quick it is just to test the different propellants. It's just almost like plug and play. You just refill the deposit, put it to a thruster, and test it. You don't need anything else. And for us, like, the question would be if there is a better option than MIM. Of course there is, because there is thousands and thousands of ionic liquids. It's just a matter of trying to find the perfect one. But we're trying a different approach, which is trying to match our system to the liquid that we are using, which is MIM. Also, of course, if another liquid is found, we will need to try to study other things like the material compatibility or the temperature behavior. And also, just to mention again, the possibility of using some ionic liquids to be used in a dual propulsion system. Some achievements during the PhD, I have presented 3 conferences in Estoril, in SPC, in IPC in Boston, and this work was also presented in EPIC a couple of weeks ago. And the work that I presented here last year regarding the temperature studies was submitted to ACTA Astronautica last month, and is right now under review process, so hopefully I will get news soon. And as for future work, the work that I'm carrying out right now regarding the ion liquids will be a more mature work, will be presented in UCAS, and the idea is also to write a journal paper regarding these topics, because I didn't mention, but 2 of these liquids, they have been never tested before, so it's also quite novel. Yeah, that's it.